This is problem 5.78. It's on page 273. The beam AB supports two concentrated loads and rests on soil that exerts a linearly distributed upward load as shown. Determine the values of the distributed load at A and the distributed load at B, WA, WB, corresponding to equilibrium. Does this problem look like? There's our beam. The soil provides a distributed load. It's about like this. WA on the left, WB on the right. There's a concentrated 24 kilonewton load that is 0.6 meters from the left and a 30 kilonewton load that is 0.3 meters from the right. Now the length of this distribution is 1.8 meters from end to end. What we'll call point A to point B. So I'm going to break up this distributed load into two parts. A uniform distributed load that has magnitude WA, and a triangular distributed load that has magnitude WB minus WA on the right-hand side. Call this distribution 1, I'll call this one distribution 2. Now the total resultant from 1 is 1.8 meters times WA. Its location, if I take x positive from A, its location is just half the length, so that is 0.9 meters over. So that's going to be, here, halfway along the way. R2, on the other hand, would be the area of that triangle, WB minus WA, that's the height of the triangle, times the base, 1.8 meters, divided by 2 because it's a triangle. So another way we could write that is 1.8 over 2 is 0.9 meters. Okay. Its location will be 2/3 of the way over, so 2/3 of 1.8 meters, and that just comes out to 1.2 meters because they made this problem nice, where all the numbers come, well, most of the numbers, I think all of them come out nice and round. So those are the resultants, and of course this one acts there. I'm not going to bother getting a resultant for the entire distribution. They didn't ask for it. They just wanted me to determine the values of WA and WB. So basically what I've got is a beam. Let me draw a free body diagram of the entire beam. We've got a 24 kilonewton load, a 30 kilonewton load, and then an R1 and R2 load of unknown magnitude, but in terms of WA and WB. So if this is point A and I sum moments about point A, counterclockwise positive, well, let's see, it looks like I'd have R1x1 plus R2x2, just using the symbols to indicate that R1 and R2 cause positive moments, minus, I'm going to plug in numbers for the 24 kilonewton and 30 kilonewton load. 24 kilonewtons, I'll drop the units, but know that R will be in kilonewtons, X will be in meters. So 24 kilonewtons times 0.6 meters, and then minus 30 kilonewtons times, well, let's see, 1.8 less 0.3, so 1.5 meters equals 0. Now let's plug in what we know. Let's see. R1 can be expressed as 1.8 WA. And let's be careful here. R1 would have units of newtons. If this is meters, then WA is going to have units of newtons per meter. Same argument for B, newtons per meter. So that's R1. X1 is 0.9. Of course, it's meters, but I'm dropping my units. So that's R1, X1. R2, X2 is, well, let's see, 0.9 times WB minus WA. It's R2, and I need to multiply it by X2. X2 is 1.2 meters. Now, if I put all of these numbers on the other side and just add them together, let's see, let me make sure that I did that. Yes, I did. Okay. So you get 59.4. Just to note that the units are kilonewton meters. So that's all of this over here, and we've taken care of this term. So, multiplying these out, you get 1.62 WA plus 0.9 times 1.2 is 1.08 WB less WA equals 59.4 kilonewton meters. And you notice I have one equation and two unknowns. If we simplify it just a little bit farther, we've got 1.08 WA negative to take from here. So if we take 1.08 from this, we get 0.54. 0.54 WA plus 1.08 WB equals 59.4. So we've got one equation, two unknowns. Let me call this equation 1. Now let me erase this distributed load diagram. And let's sum forces in the vertical direction. Well, we'd have R1 plus R2 minus 24 minus 30. Just going back to here. Just summing forces in the vertical direction. This sum, much like 30, this sum has to be 0. So R1 plus R2 has to be, put these together, move them to the other side, 54 kilonewtons. Now let's plug in what R1 and R2 actually represent. Well, R1 is 1.8 WA. R2 is WB minus WA times 0.9. That sum then, since that's R1 plus R2, comes out to 54 kilonewtons. Simplifying, notice we've got minus a WA, so 0.8, no, not minus WA, it's minus 0.9 WA, so 0.9 WA plus 0.9 WB equals 54. So if we divide through by 0.9, we'll get WA plus WB is 54 divided by 0.9, that comes out to 60. So in other words, WA can be replaced by 60 minus WB. Now we have two equations and two unknowns. Let me call that equation 2. And we could substitute in to this equation. So 0.54 WA, but WA is 60 minus WB plus 1.08 WB equals 59.4. 54% of 60 is 32.4 minus 0.54 WB plus 1.08 WB equals 59.4. And so we can say then that, notice that 1.08 minus 0.54 is actually 0.54. So 0.54 WB, that's this term and this term together, equals 59.4 minus 32.4, just moving this term to the other side. When you finally solve for WB, by taking the difference here and dividing by 0.54, you will find that WB is equal to 50 newtons per meter. Now, since WB is 50, 60 minus 50 tells us that WA is 10 newtons per meter. So that gives us WA and WB, the magnitude of the distributed load at either end of this. I suppose it's a slab or something.